We're now going to take a look at what will become the second step in our hypothesis testing process, and that is finding the critical value for each problem. So we're going to return to the three examples that we just looked at for the hypotheses, and we're going to look at adding the second step to each of those three examples. Our first example says that a researcher thinks that if expectant mothers use vitamin pills, the birth weight of their babies will increase. The average birth weight of the population is known to be 8.6 pounds. And so I'm going to go ahead and write the hypotheses as we wrote them on the last presentation. And that will take care of step one. Step two then is to draw the curve, and we are going to base this hypothesis testing on a standard normal distribution curve like we looked at in the last chapter, and determine how to shade, and then determine what we call the critical value. So one thing that is helpful is when you're trying to look at how to shade is that we want to shade the part of the curve that represents a significant difference. Now, with that in mind, let's consider that our average is known to be 8.6. And so this is our population mean. And we know that on this normal distribution curve that the population mean, that 8.6 is going to sit right in the center of the curve. And so for right now, and it's a little questionable because I'm only supposed to put the Z-scores across the bottom. But for right now, let's mark this off as the 8.6. Now, what you want to think about is doing your research. If you are this researcher, what are you going to do? And we talked about this on the previous presentation. So if I'm the researcher, I'm going to need to select a sample. I'm going to need to give the mothers in the sample the vitamin pills. And then I'm going to need to check the birth weight of their babies. And then finally, I'm going to need to calculate an average. Okay, so this is just sort of an aside so that I remember what I'm doing. Okay, so let's say that we do that, and let's say that we come up with an average birth weight of, say, 8.7. Now, that actually is an increase over the 8.6, so it is what we want in that that vitamin pill is going to increase the birth weight. But what you want to consider is, does it significantly increase the birth weight? Right, 8.7 is going to mark off maybe right about here on the curve. Would you say that that's a significant increase? In other words, would you say that that's enough of an increase that you would encourage expectant mothers to actually take these vitamin pills? And I think the answer realistically is probably no. I mean, 8.7 is so very close to 8.6 that I don't think any of us would say that that's a significant increase. Well, what if the average was, say, 9.2? And I realize that that's getting quite large, but think about that. Does that indicate a significant increase? And I think in relation to 8.6, we would probably say yes, that's a significant increase. And so where does that occur? That would occur maybe up here. And so come back to what we said. We want to shade the part of the curve that represents a significant difference. And so we definitely want to shade these here. We're saying these are significantly different. Up to a certain point. Okay, so what we're looking at here is we're basically saying, 8.7 is probably not significantly different. Maybe 8.75 is not significantly different. Maybe 8.7 is not significantly different. Or 8.8 is not significantly different. But at some point, we're going to do kind of a boundary line here. At some point, when I cross that line, I'm getting into a section where I do say that the birth weights are significantly different. And so we're going to end up shading on this right-hand side of the curve. Okay, and so I'm going to call this a right-tailed test. And we're going to come back in just a minute and add the critical value to this. But let's just talk first about simply how we decide how to shade. Okay, so let's look at the second example. An engineer hypothesizes that the mean number of defects can be decreased by using robots instead of humans for certain tasks. The mean number of defective disks per 1,000 is 18. And so again, I've written my hypotheses as we did in the last presentation. And remember that we want to shade the part of the curve where we're seeing significant difference. Okay, so remember that your mean sits in the middle, and you want to think about a significant decrease in this scenario. All right, so consider using the robots and having the number of defective disks go to, say, 17.5. Now, it is a decrease. Is it a significant decrease? Probably not. What about if the number of defects went to 17? Again, it is a decrease, but is it a significant decrease? Probably not. But what if the number of defects went to, say, 4, which would be way over here? Would that be considered a significant decrease? And we probably all would say, yes, that's significantly lower. Remember that you want to shade the part of the curve where the significant difference occurs. And so we're going to shade this section in the left tail. And so we're basically saying that for a while, it's not a significant difference. But then we're going to draw this kind of boundary line, and we're going to say as soon as I cross over that line, I've got values that are significantly less than the 18. All right, and we're going to call this a left-tailed test because we've shaded on the left side of the mean. Okay, and our last example says a psychologist feels that playing soft music during a test will change the results of the test. He's not sure whether it will be higher or lower. In the past, the average was 73. And so again, I'm going to write my hypotheses as we did in the last presentation. And then I'm going to think about what my curve looks like. Okay, so 73 sits in the middle. We only want to see a change here. Could be more, could be less, but it needs to be significantly more or significantly less. And so again, if you look at your test grades and they come in at 73.5, probably not significantly more. But if they came in at 90, that would show a significant increase. And so we'll have this section of the curve that's shaded in the right tail. Now we also have to consider in this problem the possibility that it's lower. And so again, we only want to shade significantly lower. So 72 while it's lower, is probably not significantly lower. 40, definitely lower, and probably definitely significantly lower. And so we'll shade a section on the left-hand side to indicate the scores that are significantly lower. And so on this one, we're going to call this a two-tail test because we have shaded both the left and the right tails. Okay, so now that we have a picture drawn for each one, let's go back and talk specifically about the critical value. Okay, so for a definition, this critical value that we're looking for is a Z-score that separates the shaded part of the curve from the unshaded. So in other words, on our curve, our Z-score is this value right here. Or this value right here is a critical value. And these two values would be critical values for our third example. Now, these critical values are based on what we're going to call a level of significance. And the level of significance is going to be denoted by alpha. And alpha will be given to you in each problem that you will be working. Common values for alpha include 0.05, 0.10, and 0.01. But again, you want to realize that you'll always be told what the alpha is. The other thing you need to realize is that alpha represents the area of the shaded region. Okay, so let's look at this problem. And again, they're going to tell you an alpha value. So let's suppose that they tell you that alpha is 0.05. Now remember that alpha represents the area of the shaded region. So that means that this area is 0.05. And my job now becomes, I need to use my table E to look up this Z-score that corresponds to this particular picture on the curve. Now I know that to use my table E, I actually need to know the area from 0 to the Z-score. And so if the area to the right of the Z-score is 0.05, and the area from 0 all the way to the right is 0.5, or 1/2, I can find the area from 0 to Z by subtracting. So I'm going to say 0.5 minus 0.05 gives me an area of 0.4500. I'm then going to go to table E and look up that value as an area. That area falls in my table between 44.95 and 45.05. And since it falls halfway in between, remember that the rule is to use the larger value. And so I'm going to use an area of 0.4505, which has as its Z-score 1.65. And so my critical value for this problem is 1.65. Okay, let's do the same thing for our second example. Again, you'll be given an alpha value. So this time, suppose that alpha is 0.10. Remember that alpha is the area of the shaded region. But remember that in order to use table E, you have to have the area between 0 and the Z. If this is 0.10, this is going to need to be 0.4 so that they add up to be 1/2. Looking up 0.4000 in table E, the closest area I can find to it is 0.3997. 0.3997 corresponds to a Z-score of 1.28, and that would be negative because it falls on the left side of the curve. And so my critical value in this scenario would be negative 1.28. For our last example, let's suppose that they give us an alpha value of 0.01. Now remember that alpha is the area, total area of the shaded regions. And since I have 2, I'm going to need to take this 0.01 and divide it by 2 to figure out the area of each part. So this section is 0.005, as is this section. Again, I know that in order to use table E, I have to know the area between 0 and the Z. And so subtracting the 0.005 from 1/2 gives me 4950. Looking up 4950 in my table, I see that it falls between 4949 and 4951. Since it falls halfway in between, I'll use the larger value of 0.4951. And so I can see that my Z-scores are going to be positive 2.58 and negative 2.58. And I have my critical values. Now, you'll notice in this section in your book that these are the only 2 steps of the hypothesis testing process that they cover. Hypothesis testing actually has 5 steps. The first step being to write your hypotheses, which we did in the first presentation. The second step being to draw your curve and to find your critical values, which we've covered in this presentation. And as we move into the next section, we'll look at these 2 steps in conjunction with the next 3.